Modern enterprise infrastructure operates at an immense physical scale. Thousands of isolated servers across the globe constantly exchange millions of state changes, attempting to maintain a single cohesive reality. Looking at this diagram of two network nodes, DCA and DCB, we see the baseline assumption most engineers and application developers make about Active Directory replication. They assume that sequential updates committed at the origin will commit sequentially at the destination. This assumption mirrors standard first-in, first-out, or FIFO logic, a queuing method where the first data unit generated is the first one processed. The timeline of the destination perfectly reflects the timeline of the origin, stacking perfectly in order, 1, 2, 3, 4. But Active Directory deliberately breaks this originating sequence during inbound replication. The data arrives and the transaction execution order scrambles. This out-of-order execution is not a network bug. It is a hard-coded architectural feature explicitly designed to manage distributed states across complex, multi-node environments. To understand why a system would intentionally fracture its own timeline, we have to deconstruct Active Directory's transaction logic. That requires isolating update sequence numbers, the internal counters AD uses to track changes, and defining its strict boundaries for atomicity, which is a database guarantee that a grouped update applies entirely or not at all. Ignoring this underlying architecture directly causes race conditions and unexpected behaviors in applications that rely on Active Directory for state consistency. We begin by looking at isolated domain controllers operating independently long before any replication occurs across the network. The core axiom of AD updates is that every single database change generates a unique originating update sequence number. This value permanently identifies the exact source and the exact moment that specific change was created. However, an originating USN alone is functionally useless for a destination server. It tells the server where the data came from, but it provides no instruction on how to execute a local database commit on its own hardware. This diagram shows how Active Directory solves that problem by introducing the local USN. This is a strictly internal counter that identifies a specific physical database transaction occurring on a local machine. When these distinct originating updates travel to a third, independent system, their originating histories remain permanently locked. They do not change. But the local USNs generate entirely new numbers to reflect the local rights. This dual tracking mechanism allows independent destination systems to keep a pristine record of where a change originated, while managing the dynamic physical application of that data locally. This establishes a cardinal rule for AD forensics. If two changes share identical local USNs on an object, it proves mathematically that those changes were physically applied in the exact same local database transaction. The USN mechanism decouples the chronological history of an update from the physical execution of its write sequence. With the execution sequence decoupled from linear time, Active Directory relies on database atomicity to maintain order. Atomicity is the strict guarantee that a grouped update is applied totally or not at all. Atomicity prevents catastrophic mid-update states. If a server crashes halfway through writing a file, the database system ensures that upon reboot, the object is structurally complete, existing either entirely pre-update or entirely post-update. Nothing in between is possible. Active Directory enforces entirely different atomicity limits depending on how an attribute is classified. The rules change depending on whether an attribute is non-linked, like a user's description, or linked, like group membership. On the left side of this split screen, we see the absolute rule for non-linked attributes. All changes to an object's non-linked attributes replicate together, drop in as a unified block, and receive the exact same local USN. They are committed in a single atomic write transaction. Linked attributes do not share this guarantee. Looking at the right side of the screen, we see linked attributes replicating independently. Destination controllers process these in arbitrary batches rather than unified blocks. The system limits these batches to approximately 100 multi-values at a time. Applying these strict batches means that a single, comprehensive update to an object on the originating server will span multiple, distinct database transactions over time on the destination server. By applying different atomic limits based strictly on attribute type, Active Directory actively forces a single logical update to splinter into multiple physical transactions. To see how this splintering occurs in transit, consider a specific scenario. Two objects receive simultaneous updates to one linked attribute and one non-linked attribute at the exact same time. The system must now package these 4 discrete updates for network transmission to a destination server. In this diagram, we have our empty replication packet and the 4 discrete data blocks hovering outside it. To optimize state consistency, Active Directory explicitly prioritizes updates to non-linked attributes over linked attributes during packet assembly. The strict sorting logic strips the updates from their originating chronological order. The 2 non-linked blocks snap to the front of the packet, and the linked blocks are pushed to the back. The resulting internal architecture of the data packet forces non-linked values to lead. This effectively splits the attributes of a single object across the payload, separating them by priority rather than by the time they were created. This prioritization mechanism physically fractures the chronological integrity of the initial update to ensure critical structural data arrives first. This sorting logic creates a severe system stress test. What happens when the sheer volume of high-priority, non-linked data exhausts the replication packet's physical capacity? As we see here, a cascade failure occurs. All non-linked values for an object swell to fill the primary packet. Because the space is exhausted, their associated linked values are forced out and orphaned into subsequent network packets. We can track the physical arrival of these separated packets. Packet 1 arrives at the destination node and immediately commits to the database, generating a new local USN. Packet 2 remains suspended in network transit. The destination server writes transactions based purely on how data is received. Because the non-linked attributes arrived in the first packet, they commit immediately in transaction 1. The linked attributes will not commit until transaction 2. The object's state finalizes entirely out of its originating order. A final safeguard compounds this out-of-order execution. Parent-child relationship rules override inbound sequencing, guaranteeing that object creation strictly precedes the application of any links to that object, regardless of when the packets arrive. The strict volume limits of network packets, combined with aggressive attribute prioritization, guarantee that complex updates will routinely execute as out-of-order local transactions. Out-of-order execution on destination domain controllers is a deliberate, highly engineered feature. It is the intended behavior of the system under load. This visual comparison matrix shows the architectural intent. On the left, a linear timeline fractures under stress. On the right, prioritizing structural integrity keeps the distributed database locked together. Maintaining this web is exponentially more critical than preserving linear time. For systems engineers and application developers, this mandates a strict rule. Never build external tools that rely on strict first-in, first-out update sequence replication from Active Directory. Active Directory perfectly guarantees eventual consistency. But the transition of states between updates will vary wildly across the global network, depending on packet sizes and local processing times. Developers must build their logic on the relational inferences guaranteed by Active Directory's discrete atomic boundaries, instead of timestamps. In practice, this means if you design Attribute 1 and Attribute 2 to update together as an atomic non-linked group, positively observing Attribute 1 mathematically guarantees the state of Attribute 2. The local database will not allow one to exist without the other. True architectural mastery of Active Directory requires abandoning the illusion of sequential time and designing exclusively for the resilient, decoupled logic of atomic states.